Hello and welcome. My name is Mukundan Sridharan, and I'm going to present you the KanseiGenie testbed, and I'm going to show a small demo on how to use the web interface of the testbed to configure and run a experiment. First, a small introduction about the Kansei testbed. So the Kansei testbed is the world's largest sensor networking testbed, located at the Ohio State University, and the project is headed by Professor Anish Arora. It has four different hardware arrays. It has 96 numbers of each of the start gates, the XSMs, and the iMode2 platforms. So the Stargate is embedded Linux platform, and the XSMs are derived from the Mica 2 modes. And it also has 384 TLOS Bs arranged in a 24 cross 16 grid topology with 2 feet uniform separation. The TLOS Bs also has a 3 dB attenuator attached to each of their antennas to decrease the radio range of the nodes. The focus of this video and the demo will be on what we call the genification of Kansei, and but what we mean by that is the modifications that we have done to the architecture of Kansei to make it compatible with the Genie specifications. The picture on screen shows the architecture of KanseiGenie. It consists of 4 different components. So the first, the aggregate managers, so which is in charge of managing the hardware array, and which in turn consists of 4 different modules: the slice manager, the experiment manager, the O&M manager, and the measurement manager. So each of this managers corresponds to the to one of the to the functional planes of Genie. The second component is the site or the policy authority. The third is the clearinghouse, and fourth is the researcher portal. So we will be focusing on the researcher portal today, and we will see how we can use the portal to create and configure experiment, and how to run and extract the data back from the portal. So the in terms of implementation, so the researcher portal is implemented on top of of a web service layer, which implements the specific APIs of the aggregate manager and the site authority. So the portal itself is implemented in PHP, and the site authority and the aggregate manager are implemented using JBoss, and using the JBoss based web services. In the current implementation of KanseiGenie, the ticket / slice creation calls between the researcher portal and the clearinghouse is being bypassed, and the portal is directly talking to the site authority to create the slice. So similarly, the RSpec advertisement from the site authority is going directly to the portal, because our implementation of the clearinghouse is not yet complete. We now see the researcher portal interface on screen. So the homepage of the portal gives us some statistics about the number of nodes available on the testbed, and if there are any nodes that are down or failed. And it also gives us some information about the statistics about the number of experiments that are currently running, pending, or that have been completed in the last 1 day and 1 week. So in order to use the portal, the first thing we need to do is to log in. So there are essentially 5 basic steps to configure and run an experiment. So the first thing is to check if there is any experiments that is currently running. So we can go to the testbed status tab, and which will show the status of the jobs that are currently running. So the next thing we do is we need to upload the file that we will be using, the executable file that we'll be using on a particular array that we will be using. So for this demo we will use the telos B array, and we will upload an executable that is created using the TinyOS 2 operating system, and then we will choose the telos B as the platform. So this application simply tries to measure the link quality that is on each node. So each node periodically sends a message, and it logs all the messages that is received by a particular node, and which we will use we will use the data logged on each node to calculate the link quality on each node. So we just uploaded this file, telosrange.exe, and this is for the telos B platform. So next what we do is we create a slice for the user. So a slice is a logical representative of the user in Genie. So to create a slice, we just enter its slice name, then we specify the user's email ID. So and we click create slice. So and we just created this test slice for the user Anish. So what just happened is so the portal interacted with the site authority and created this test slice. So this was originally meant to be the portal was supposed to interact with the clearinghouse to create slices, but in the current implementation we are bypassing the clearinghouse. So the next step to do is to create an experiment RSpec. So that is the list of all the resources that we will be using for the current experiment, and a particular RSpec is tied to a particular slice which belongs to a user. So since we will be using the telos B array, we will create a telos B RSpec, and as we see, a single owner can own multiple slices, and we can choose which one of the slices that we want to associate with a particular RSpec. So in this case, we will use the test slice, and we will create an RSpec which has all the 384 telos Bs. That is, we will run an experiment that on all the 384 telos Bs available on Kansei, and we just choose all the nodes and we click create telos B RSpec. It's taking a little bit time because it is talking through web service APIs to the site authority to create the RSpec. The RSpec creation just completed, and we see that it has created an RSpec that involves all the nodes from 101 to 484. So while a user is creating an RSpec, so he can refer to the topology of the particular array. For example, this figure shows the topology of the telos B modes arranged in a grid, starting from 101 till 484, and the nodes that are shown in red have some kind of fault and they are not currently available, so the users can avoid choosing those nodes. So if you choose a node that has failed, the Kansei scheduler will automatically skip deploying a program on those modes, so you don't have to worry if you don't have to necessarily avoid those nodes. So next we will configure an experiment using the aspect that we just created. So this is the aspect that we just created, and we also see that the user has another aspect which is for the XSM specs, but we will use the telos B array. So we choose the aspect that we just created, and we will enter the other details of the experiment. So we enter a username. So the username is different from the login name because we generally give a single login name for a research group where multiple users can use the same login. So you can enter a username, and you can enter a description of the experiment that you want to carry on. And you have to enter a username. So next you can specify the date and time at which you want to the job to be scheduled, and you have 3 different options while choosing this. So if that particular date and time is not available, the first option, next available, will automatically schedule a slot, the next available slot for that particular hardware array. If you click absolute, then it means that you want only that particular time, and if that time is not available, you will just get an error. And if you click force, then it will, and if the user has enough privileges, then the scheduler will try to force, if a job is already running, it will try to preempt that job and try to deploy this job instead. So, and you can choose the length of the time for which you want to run a particular experiment. So we will choose 10 minutes, and here now we see all the files that have been uploaded for the telos B array, and this is the file that we just uploaded, and this is the aspect that we chose for this particular experiment. And we will click the set tmode IDs option, which gives the option of setting the mode IDs individually on each of the modes. And the last option, the telos B target communication, specifies the logger that we are going to use for this particular experiment. So depending on the on the type of executable that we have created, for example, whether it's a TinyOS 1 executable, TinyOS 2 executable, or the Kansei executable, we can choose a particular logger. And the Kansei testbed is in general, it's a platform independent testbed, which means you can schedule executable created using any operating system or platform on Kansei. But currently we support these 3 operating systems where we provide automatic logging functionality. But in theory, you can run executable from created using any platform. So next we click the configure experiment, and we have successfully configured an experiment, and the web interface automatically takes us to the dashboard. So the dashboard is the place where we can interact with a particular experiment. So once you have configured an experiment, you can start an experiment, or you can cancel an experiment. And once the experiment is has finished running, you can look at the logs, or you can download the output. For example, these experiments have already completed, and you can either look at their logs, or you can download the output of the particular experiment. So now we will go ahead and start this particular experiment. So once you have started an experiment, if you go to the testbed status, so it shows up under the experiments ready to execute. So what this means is now the this particular experiment is ready to run, and the Kansei scheduler will automatically pick up this particular job, and it will schedule the job on all the nodes that we have chosen for this particular experiment. So the Kansei scheduler is right now deploying the job on the nodes chosen, and once the deployment is complete, it will show up under job under experiments currently executing. So as I said, the job number 37 has moved from ready to execute to currently executing, which means the scheduler has deployed this job. So if we go to the dashboard, we will see that the job is currently running, and if you think that you have made some mistake in configuring the experiment, you can stop the experiment, and it also shows you a log which you can look at to see the information about the deployment. So if in case you don't get the output that you were expecting, this job log will give us information about what went wrong. So we will now wait for the experiment to get over, and we will download the output of the experiment. The experiment is now complete. The job number 37, which we scheduled, is now complete, and we see that we can download the output of the job. So we'll go ahead and download the output, and we will save the file. So what is being logged and extracted is that any data that is written to the UART port of the Telos B is automatically logged, and it's retrieved after the experiment is complete, and it's zipped and can be downloaded after the experiment. So since we scheduled the experiment on 384 nodes, it's going to take some time to download all the logs. So let's wait. So the downloading is now complete, and so we will use a Perl script to extract the data from the zipped file. The data extraction is now complete, so it creates a directory called data, and as we can see, it is extracted all the data from the 384 nodes from 101 to 484. So we'll just look at one sample log file to see how it looks. So so the first two fields of the log file is the Unix timestamp in seconds and microseconds, and the rest of the data is what was returned to the UART port. So so we'll just show so we'll just show the link quality data that we plotted into a graphical view of the current experiment. So as we can see in this figure, as we click on each node, we can see that it has links. It shows the links on that it received from each of the other nodes, and the color of the links represent the quality of the link. For example, this green link means that the quality was good, whereas these red or orange links means that the link was not that good. So so this example also shows that how you can control the topology of a particular experiment by using a combination of the external attenuator and also the software power levels on the radios. So even though we use the entire nodes for the test, we see that the number of neighbors that each node has quite is quite small, and the number of good neighbors it has is actually very less, and it has quite a number of nodes that are that are what we call the long links. So that's the demo that we wanted to show, and thanks for watching the video, and we hope all of you will use our test bed. Thank you.